Some things move us emotionally. One is music. At a musical concert, we may be moved to tears, and then we realize the music we hear can be seen in the pattern of notes we call sheet music. All quite wonderful. A similar emotional experience is seeing the stars on an extra clear night, and similarly wondering if it all follows a pattern to the universe. And we wonder what that pattern might be. As it happens, Isaac Newton discovered the pattern, which accounts for the roundness of planets and stars, how they pull on one another, and how each shining star pulls itself into a tight ball of gas. That pattern is represented in a simple physics relationship between force, mass, and distance, which is much less complex than the simplest sheet music. It is called the universal law of gravitation. Would you like to see the pattern? Here it is. A physics student can learn to read this pattern just as a musician can read the notes on a page. That's what we'll do on this screencast. First of all, the law states that there's a force of attraction between all pieces of matter. The relationship here treats two bodies of matter at a time. The attractive force between two bodies, say of mass m sub 1 and mass m sub 2, is proportional to the product of their masses. The d square in the denominator tells that the force varies as the inverse square of the distance between the centers of the bodies. The story of how Newton came to discover this law is fascinating, and we won't get into it here. Instead, we'll just see if we can read its sheet music. We'll begin with a simple situation. What happens to the force between two planets if the mass of one of them, say m sub 1, is doubled while the separation distance remains the same? Can you see the force is doubled? I hope so. And what happens to the force between them if both masses, m sub 1 and m sub 2, are doubled? I hope you can see the force is 4 times as much. The symbols guide our thinking. Now let's consider distance, the inverse square law. Consider a pair of the same planets when the distance between their centers is doubled. How is the gravitational force between them affected when they're twice as far apart? Here we have, is this right? No. We have to include the 2 in the distance to be squared. We square the 2, which, gives us 4d squared in the denominator. Can you see this results in 1/4 the original force of gravity? And what happens to the force if the planets are 10 times as far apart? Can you see this results in 1/100 the original force of gravity? Or instead of the planets farther apart, consider them closer. What happens to the force between planets when their distance of separation is half as much? Can you see that the force increases with closeness? That the force isn't twice as much, it's 4 times as much? Again, the inverse square law. A yum-yum law once you get the hang of it. About a century after the time of Newton, careful measurements of gravitational force in the laboratory showed that for a pair of masses at a carefully measured distance, the ratio of gravitational force F to the product of their masses divided by distance squared produced a number. The same number whatever the masses and distances involved. In standard units of newtons, kilograms, and meters, 6.67 times 10 to the minus 11th. A very tiny number, indicating the tiny force of gravity between objects small enough to be in the lab. This is similar to the circumference of a circle C divided by its diameter d, always producing the same number, 3.14, which we call pi. Pi has no units because distance divided by distance in the same units cancels. Whereas pi is for circles, the constant of proportionality for gravitational force, that is, the universal gravitational constant, is the capital letter G, and it does have units. With g, we convert the proportional form of Newton's law to the exact equation. To emphasize that the distance between objects is a radial distance, straight line between their centers, it's common to use the symbol r in place of d. The symbol r stands for radial distance. If you were asked on an exam to cite the units of g, could you do it without memorizing it? Yes, you can. You simply let the equation guide your choice of units. We see force in newtons, masses in kilograms, kilograms square actually, and d squared in meters squared. So the units of g are Newton meter square per kilogram square. If you know the equation for a quantity, you need not memorize its units. They follow from the equation itself. Again, equations guide thinking. Let me leave you with a question. Suppose an astronaut lands on a planet that has twice the mass of Earth and twice the diameter. How does the astronaut's weight differ from that on Earth? Let Newton's equation for gravity guide your thinking. Until next time, good energy.
Not many people still believe the Earth is flat. If we view the Earth's horizon near the ocean from a high elevation, like from an upper floor of a high-rise building, Earth's curvature can be seen with the naked eye, especially with the aid of a meter stick held at arm's length aligned with the horizon. We see that our Earth's surface is not flat but curved. We can do more with a meter stick. Hold it vertically with one end on the ground. If it's a sunny day, the meter stick casts a shadow. If you're located in a region where a noontime sun is directly overhead, no shadow is cast. With this common knowledge, the roundness of Earth was measured. The first person credited for measuring the roundness of Earth was the Greek scholar and geographer ERATOSTHENES of Syene in about 235 BC. He was a man of learning and the chief librarian at the Library of Alexandria in Egypt. From library information, Eratosthenes learned that the sun is directly overhead at the summer solstice in the southern city of Syene, the present-day site of the Aswan Dam. He knew this because at this special time in June, sunlight shining straight down a deep well in Syene is reflected straight up again, the only time the sun's reflection can be seen in the well. He correctly assumed that the rays from the very distant sun are essentially parallel to one another by the time they reach Earth. So when the sun is directly overhead in Syene, it is not directly overhead in Alexandria, as evidenced by the shadow cast by a tall vertical pillar there. He measured the shadow and found it to be 1/8 the height of the pillar. Said another way, at this special time, the pillar was 8 times taller than the shadow it cast. This corresponds to a 7.2-degree angle between the pillar and the sun's rays. He further reasoned that if a line along the vertical well in Syene were extended into Earth, it would pass through Earth's center. Likewise for a vertical line in Alexandria, or any point on the spherical Earth. Both verticals extend to the center of Earth. And get this, these lines to Earth's center form the same 7.2-degree angle that the sun's rays make with the pillar at Alexandria. The distance between Syene and Alexandria, quite flat and frequently traveled, was measured by surveyors to be about 5,000 stadia, 800 kilometers in today's measurements. So remarkably, Eratosthenes reasoned that the 800-kilometer segment between the two cities at Earth's surface is subtended by 7.2 degrees, and likewise for all other 800-kilometer segments around Earth. How many 7.2 segments make up Earth's circumference of 360 degrees? The answer is 50. That's right. So Earth's circumference must be 50 times greater than the 800-kilometer distance between Alexandria and Syene. Earth's size was then known, having a circumference of 40,000 kilometers, quite close to today's accepted value. We can arrive at the same conclusion a different way. Ratio and proportion, comparing very nearly similar triangles, the small and the large green ones. Both triangles have equal angles and equal ratios for their sides. Recall the pillar 8 times as long as its shadow? Similarly, equal ratios tell us that Earth's radius must be 8 times the distance between the two cities. And Earth's radius, remarkably, equals 8 times 800 kilometers equals 6,400 kilometers, very close to its presently accepted value. How about that? If we know Earth's radius, we know its circumference, c equals pi d, or 2 pi r. Earth's circumference is some 40,000 kilometers, in general agreement with Eratosthenes' findings. Today, Eratosthenes is remembered for his amazing calculation of Earth's size, using only good thinking and a bit of trigonometry. 1,700 years after Eratosthenes' death, Christopher Columbus studied Eratosthenes' findings before setting sail for the New World. Rather than heed Eratosthenes' findings, Columbus chose to accept more up-to-date maps that indicated Earth's circumference as 1/3 smaller. If Columbus had accepted Eratosthenes' larger circumference, then he would have known that the land he discovered was not China or the East Indies, but rather a new world. I want to leave you with a question. For a smaller Earth, as Columbus thought, but with the same 800-kilometer distance between Alexandria and Syene, would the shadow cast at the solstice noon by the pillar in Alexandria be longer or shorter? Think about that. Good energy.
Newton's law of universal gravitation is shown here in equation form. The gravitational force between Earth and Moon is easily calculated by putting the masses of each and the distance between their centers into this equation, along with Newton's gravitational constant g. A question arose in the minds of many investigators of science during Newton's time and after. That is, how is it possible for two objects such as the Earth and the Moon to interact when not in contact with each other? Newton himself couldn't imagine an influence reaching out through nothingness. Today we look at the concept of a force field. The Moon interacts with the gravitational field of planet Earth. Surrounding Earth and every body with mass is a gravitational force field. We show the field with sample lines of force, in orange, that emanate from Earth, originating at Earth's center, not indicated here, and emanating outward indefinitely. We'll return to force fields when we study electricity, where we'll see the importance of the electric field in electrical interactions. When a bit of mass is in the vicinity of Earth, it experiences a force. This is the force due to gravity as expressed in our equation for gravity. If we divide this force by the mass of the object being pulled, let's call it m sub 1, we get g multiplied by m sub 1 times the mass of the Earth divided by the radial distance squared, all divided by m sub 1, which after canceling the m sub 1's equals g mass of the Earth divided by radial distance square. Now here's the interesting part. Recall from previous lessons that F over m is Newton's second law for acceleration, and that the acceleration due to gravity at Earth's surface is 10 meters per second square. If we plug Earth's mass and its radius and the gravitational constant g into this equation, we get 10 newtons per kilogram, or more precisely 9.8 newtons per kilogram. We know the acceleration due to gravity at Earth's surface has this value. Recall that newtons per kilogram is equivalent to meters per second square. Yum confirmation of what we've previously learned. Now we can define the strength of Earth's gravitational field at any radial distance as G equals G, mass of the Earth, divided by radial distance squared, where we used bold-faced G as the symbol for Earth's gravitational field. G, like acceleration, is a vector quantity and is strongest at Earth's surface and weakens with increasing distance from Earth's center via the inverse square law. Let's look at how distance affects Earth's gravitational field. We construct a graph of field strength versus distance from Earth's center. Red letter R shows the Earth's radius. As said, the field is maximum at Earth's surface. We plot this point with the purple dot. At a distance twice Earth's radius, the field is 1/4 as strong as at the surface. Another purple dot. At a distance 3 times Earth's radius from the center, it's 1/9 as strong, and so forth. We connect the dots and see a graph that clearly illustrates the inverse square law. An interesting question. What would be the strength of the field in a small cavity in Earth's center? Can you see that a mass placed there, orange dot, would be pulled equally in all directions? Since force is a vector quantity, can you see that the forces there would cancel to 0? And hence the gravitational field at Earth's center would be 0? That's correct. Earth's gravitational field at its center is 0. So another dot on our graph at the 0 point. Consider a vertical shaft down to a point halfway to Earth's center. To progress further, let's assume Earth's density is uniform throughout, although it's really denser with depth. This gets interesting. A small mass halfway to Earth's center, shown by the orange dot, would be pulled downward by Earth's mass below, but upward in all directions by masses in regions above r/2. I'm taking a shortcut and telling you what happens here. It so happens that the pulls by Earth's mass at radial distances above the halfway point, r/2, cancel. That's right, the resulting gravitational force acting on a mass at the bottom of the shaft is due only to Earth mass below the r/2 region. Earth's gravitational field halfway to its center is half what it is at the top of the shaft, at Earth's surface. We plot this dot at half maximum field strength and half Earth's radius, r. The gravitational field between the surface and center for a uniform density Earth is linear, so our graph shows a straight line for the field within Earth. So if you apply the equation for Newton's law of gravity inside Earth, or calculate Earth's gravitational field inside Earth, the mass you use is the mass in the sphere below radius r/2, which I show with this cross-hatching. And at the center, where r equals 0, where there's no Earth mass below you, and where forces in every direction cancel out, Earth's field is 0. So there's no field at the center due to the mass comprising planet Earth. But suppose a giant massive spaceship landed on Earth's surface. If you were in a cavity at Earth's center, would you know about it? It turns out the answer is yes. You'd be gravitationally attracted to the spaceship as if Earth's mass didn't exist. So Earth's mass, or any mass at all, doesn't shield gravitational force. Not at all. Is this interesting or what? I'm covering a lot of ground here, and you may work out the math to confirm what we've covered. In the next lesson, we'll consider a tunnel bored completely through Earth, and what would happen if you fell into such a tunnel. For now, I want to leave you with a question. In a cavity at Earth's center, do you experience the gravitational pull of the sun? Think about that. Until next time, good energy. In the previous lesson, we showed how an Earth's gravitational field decreases beneath Earth's surface, and how at Earth's center the field is zero. Now let's consider a tunnel bored completely through Earth, say from the North Pole to the South Pole, so rotational effects are minimum. If you fell into such a tunnel through Earth, what would be your fate? Would you fall to the center and then stop, because the force of gravity at the center and Earth's field there is zero? No way, for you'd have considerable momentum, right? Or would you shoot out the other side like a cannonball? No way. Where would this additional energy come from? In the interest of time, I'll just tell you what would happen, if you don't already know. If we pretend that Earth has a uniform density, you'd speed up in your fall toward the center at a uniformly decreasing acceleration and whiz past the center at maximum speed. Then you'd continue up the other side. How far? To your initial height, but at the opposite end of the tunnel. And if you didn't grab onto the surface, you'd fall back and continue your motion to and fro. You'd oscillate in what we call simple harmonic motion. And the time for a round trip would be about 90 minutes. Quite remarkably, an Earth satellite, shown here in purple in close circular orbit, also takes the same time, about 90 minutes for a complete single orbit. Is this a coincidence? The answer is no. For as it happens, a satellite and you oscillating in the tunnel would move to the same rhythm and keep up with each other. In fact, your simple harmonic motion is a projection of uniform motion in a circle. You and the satellite have the same period of motion. You both make your trips in the same time. Let's look at this in detail. Here's a dashed reference line. Let's raise it a bit so it lines up with the satellite. And pretend you begin your fall where the satellite is. Now you fall to the 1/4 point down the tunnel. Here's the bit. During your falling time, the satellite progresses to here. Note the reference line, a match. And during the time you reach the halfway point, the satellite progresses to here. 1/4 its way to making a full circle, as seen by the reference line. And during the time it takes you to reach the 3/4 point, the satellite moves to here. Again, the reference line coincides with both you and the satellite. And in the time it takes you to reach the end of tunnel, guess what's there? That's right, the satellite. Another reference line match. And not surprisingly, the process repeats itself as you fall in the opposite direction to your starting point. And here's you making 3 cycles in simple harmonic motion. And here's the satellite making 3 orbital paths. Can you imagine these occurring simultaneously? Let's look at a 3/4 view of the satellite orbiting Earth. You wouldn't be able to see the satellite on the other side, which I'm showing here darkened. You can imagine you falling in simple harmonic motion all the while, right? Aha, if we look at the satellite motion not in a 3/4 view, but end on, we see both you and the satellite in yum harmony. My artwork is crude compared with what an animation studio would do with this idea, but I'm hoping your imagination puts all this together and the concept is clear to you. All this is indeed fascinating, yes? Or we should say, yum yum. Let me leave you with a question. When you whiz past the center of the tunnel through Earth with maximum speed, how does this speed compare with the constant speed of the satellite in close circular orbit? Think about that. Until next time, good energy. For centuries, people have wondered about the role of the moon on ocean tides. Here's the moon, an empty space. Not quite so empty, for in its vicinity, let's suppose there's a giant blob of water.
For the moment, we'll assume both are at rest. If no external forces act on the giant blob, it's pulled inward by both surface tension and its own gravity to take the shape of a sphere, the shape having the least surface area. But there are external forces on the water. The moon exerts gravitational forces on the blob and forces that are not uniform. Since the force of gravity between two bodies varies as the inverse square of their separation distance, the moon pulls harder on the parts of water closer to the moon than on parts farther away. If the body of water is closer to the moon, the elongation is more pronounced. Not only are the forces greater, more importantly, the difference in forces between the closest and farthest parts is greater. Opposite sides of the blob seem to be stretched apart. Let's move the water back a bit and put planet Earth in the middle of it. And let the planet spin, say 1 rotation each day. Looking down on the North Pole and watching Earth rotate, an observer at the seashore notices that the water is deep here, a high tide. Oh, notice the water is becoming less deep. And here we're at low tide, the best time to dig clams at the beach. Then the water begins deepening again, and before you know it, we have another high tide. The cycle continues. This computer animation makes this clearer. Nearer the moon, we see a greater stretch. Put a solid body inside the blob, move it out a bit, and here we see a North Pole view of Earth rotating daily beneath the ocean bulges. So with each rotation of Earth, we get 2 high tides and 2 low tides.
So we see how Earth is elongated by the difference in lunar pulls on it. The elongation is on opposite sides of Earth, so it doesn't make sense to think that the elongation is only on the side of Earth that faces the moon. A corresponding elongation occurs on the moon as well, even though it's solid. Consider the elongated moon, as I'm drawing, very much exaggerated to help me explain an age-old question. Why does only one side of the moon face us? The moon, like all bodies that rotate, rotates about its center of mass, shown by this purple dot. Here's a situation where the center of mass and center of gravity don't coincide. Because one side of the moon is closer to the Earth than the other, the close side is more gravitationally tugged toward Earth than the farther away side. This results in Moon's center of gravity being somewhat closer to Earth than its center of mass. I draw this with the red dot. And a purple dot for Earth's center of mass. This red vector from the Moon's center of gravity is the gravitational force that Earth exerts on the Moon. The Moon's long axis, through both its centers of mass and gravity, is shown by this white dashed line. The result is a torque about the Moon's center of mass, which tends to rotate the long axis of the Moon into alignment with Earth's gravitational field. We see the same behavior with a compass needle that aligns with a magnetic field. Once aligned, the torque no longer exists. The alignment of Moon's long axis continues as the Moon circles Earth. We say the Moon is tidal locked to Earth. How about that? Now, getting back to ocean tides. It so happens that the Sun also plays a role in ocean tides. Because of its vast distance from Earth, the difference in its poles on near and far sides of Earth are much less than Moon's difference in poles. Although less than half as effective as the Moon in raising tides, Sun's influence is there because it's so massive. Most noticed when the Sun, Moon, and Earth are aligned. Here we see the Moon in its new moon position. Tidal influences of Sun and Moon coincide when this alignment occurs, producing extra high tides and 6 hours later, extra low tides. At times when the alignment is perfect, so the Moon casts a shadow on Earth, we have a solar eclipse. But that's another story. These greater than average tides are called spring tides, although they have nothing to do with the spring season. Spring tides occur at or near the time of a new or a full moon. When the moon is not in line with the sun, when it's positioned 90 degrees to the line between sun and earth, tides due to the moon and sun partly cancel each other. That occurs when an observer on Earth sees a half moon in the sky. How do you think tides are affected at this time of month? Did you say smaller high and low tides then? If so, you're correct. These tides are called neap tides. Our treatment of tides is simplified. Average high tides are only a meter or so above the average surface of the ocean. So the bulges we depict are greatly exaggerated. And why the tidal bulges don't line exactly with the moon or sun, why they don't occur at the same time each day, and why variations in tides occur in different parts of the world, these all make up another story, a fascinating one. I leave you with a conservation of water type question. Suppose you go to the beach to dig clams at the time of an extra low tide. Is it reasonable to assume that in about 6 hours the high tide that follows will be extra high? Think about that. Until next time, good energy. This is an actual sketch made by Isaac Newton. It shows the paths of a cannonball fired at different speeds from the top of a hypothetical mountain. Newton asserted that if fired fast enough so the curved path of the cannonball matched the curvature of Earth, it would fall indefinitely. Here's a similar sketch. Let's call this Newton's mountain, which we'll imagine is high enough to be above the effects of air drag. Let's put a cannon at the top of the mountain. If there were no gravity, then a horizontally fired cannonball would follow a straight line path. But there is gravity, so a fired cannonball would fall beneath this straight line path. Let's fire one. Little higher speed. Higher speed. Let's fire at really high speed. My goodness, look at this. The cannonball would... Got to get the cannon out of the way. But the path matches Earth's curvature and the cannonball falls all around the Earth without ever touching the ground. It's an Earth satellite. Newton made calculations of what this speed would be and realized that cannonballs could never be fired that fast. Rocketry wasn't the order of the day back then, and certainly he wasn't hip to multi-stage rockets. So Newton did not envision humans ever putting satellites in orbit. What was the enormous speed that Newton calculated? I think you can calculate that speed also in your head without a calculator if you let me guide your thinking a bit. There are two things you need to know. Number one, that an object falling beneath a straight line path falls a vertical distance of 5 meters in its first second of fall. That's the distance an apple would fall in 1 second if you dropped it from the roof of your house. The second thing you need to know is how round Earth is. A geometrical fact about the curvature of Earth is that its surface drops a vertical distance of 5 meters for every 8,000 meters tangent to its surface. 8,000 meters is 8 kilometers. Consider a portion of Earth in a desert region, where the land is flat and without obstructions. Let's mount a laser on a tripod about a meter above ground level and shine a laser beam horizontally out across the desert floor. Due to Earth's curvature, the beam downrange would be higher above the ground than at its starting point. At 8 kilometers downrange, the beam would be 5 meters above its starting level. This may prove interesting. Now suppose we replace the laser with a super cannon. one that can fire cannonballs with incredibly high speeds. Furthermore, we pretend there is no air resistance. What we want to do is calculate what Newton calculated, but in a different way. To begin, suppose we fire the cannonball at a speed of 2 kilometers per second. Then at the end of 1 second, with no Earth gravity, the cannonball will have reached 2,000 meters downrange. That's 2 kilometers. But there is gravity and it falls below this point. How far? That's right, 5 meters. But it would hit the ground before this happened. If the cannonball were to be airborne during this time, we'd have to dig a trench in the sand. Clearly, 2 kilometers per second is not fast enough for orbit. Let's fire the cannonball at twice the speed, at 4 kilometers per second. This time, the cannonball travels 4 kilometers during this second. But again, it would hit the ground before 1 second elapses, unless we dig another trench. I hope you can see where this is going. Let's try 6 kilometers per second. Is this fast enough so that we don't have to dig another trench? No, again, we'd have to dig sand out of the way, but notice, not as deep. Is there a speed wherein we don't have to dig a trench at all? And what is this speed? Can you see that if it gets 8 kilometers downrange in 1 second and falls 5 meters below where it would go with no gravity, that no trench would be necessary? What's the speed? I hope you said 8 kilometers per second. At 8 kilometers per second, it never touches the ground. Note something interesting. Since there's no air drag to slow it down, when the cannonball gets to the 8 kilometer distance, it's moving just as fast as initially. So it would repeat falling beneath a new tangent every second. Unless some force interrupts it, it would fall indefinitely. It would be an Earth satellite. Yum. Now 8 kilometers per second doesn't sound fast, but convert it to miles per hour and you get 18,000 miles per hour. At higher elevations, orbital speed is less. For example, the International Space Station orbits at an average speed of 7.7 kilometers per second, a bit less than 8 kilometers per second. Is the space station above Earth's gravity? No. What it is above is Earth's atmosphere, most of it anyway. Because of slight air drag every once in a while, the space station has to be given a boost in speed. Astronauts inside are in a continual state of free fall, which feels like there's no gravity. But Earth gravity at that altitude is nearly 90% of what it is here at Earth's surface. Without it, the space station and all Earth satellites would fly off into straight-line paths. Let me leave you with a question. Why does a satellite in circular orbit maintain a constant speed? And tie this to your answer as to why a bowling ball rolling along an alley also has a constant speed. Both the satellite and the bowling ball are pulled downward by gravity. So why don't they speed up? Until next time, good energy. Consider our planet Earth in space, and these sample positions of an Earth satellite in circular orbit. Before the idea of inertia was understood, people thought that a force in the direction of motion was responsible for motion. They imagined angels pushing on the planets. Newton changed all that and taught us that the only force acting on a satellite acts toward the body it orbits. That's the gravitational force. And what if this force disappeared? Then the satellite would fly off in a straight-line path. No force, no orbital path. Note that each of the force vectors are the same size and point to Earth's center. Same size because the satellite circles at the same distance from Earth. Note also that they're perpendicular to the orbital path. The 90-degree angle means there's no component of force along the orbital path, which further means no change in speed. From an energy standpoint, that means no change in kinetic energy. And since distance remains constant, no change in potential energy. So both kinetic energy and potential energy are constant all along the orbital path. So a satellite in circular orbit effectively coasts at an unchanging speed all the way around and around and around. Now things are different for a satellite in an elliptical orbit. Consider these sample positions for such a satellite. Since the distances from Earth are different, the forces are different. Weaker far from Earth and stronger when closer, in accord with the inverse square law. So the speeds are different also. Kepler was the first to discover the elliptical paths of planets about the Sun early in the 17th century. He discovered that planets travel fastest closest to the Sun and slowest farther away. But he had no explanation as to why. Just as a projectile tossed upwards slows as it rises and speeds up as it returns, so it is with any satellite. Kepler never viewed a satellite as a projectile, that planets are projectiles falling around the Sun, just as our moon is a projectile falling around Earth. This way of thinking escaped Kepler. Let's talk energy conservation. The sum of the potential energy and kinetic energy at any point along the satellite path is the same as at any other point. Hence, where the kinetic energy is greatest, potential energy is least, and vice versa. We can look at the change in the speed by considering the components of gravitational force along the satellite path. The component perpendicular to the satellite path, shown as a white vector here, doesn't affect speed, but changes the direction of motion, curving it away from a straight line path. More interesting is the component along the path, which we make purple here. That component of force changes speed. When in the same direction of motion, speed's increased. But here on the other side, the purple component slows the satellite. That's because the satellite is going against gravity there. So for our satellite, we see it has the least speed farthest from Earth and the most when closest. It falls around and around indefinitely. I want to leave you with a question. What becomes of the purple component of force along the satellite's path when the satellite is closest to and farthest from Earth? And more important, why? Until next time, good energy.